In last lecture, we completed our chapter 1, that was basics of thermodynamics. In this chapter, we will start chapter 2, that is temperature. So we will see the definition of temperature. So temperature is a property which distinguishes thermodynamics from other sciences. Okay, so temperature is specifically for thermodynamics only. Okay, so the first topic in chapter temperature we will study is zeroth law of thermodynamics. Okay, so zeroth law is was introduced by Fowler in 1931. Okay, so we will see what is the definition of what is zeroth law of thermodynamics. So according to zeroth law of thermodynamics, if a body A is in thermal equilibrium with body B, and also separately with body C, then B and C will be in thermal equilibrium with each other. So we can remember it like this. Let me draw. Okay, so let's say this is body A, and it is said that body A is in thermal equilibrium with body B. Body is in thermal equilibrium with body B and also separately with body C. It means that body A is in thermal equilibrium with body B and body C separately. Okay, so what happens when both B and C are in thermal equilibrium with A separately? So we can deduce from here that B and C are also in then B and C will also be in thermal equilibrium. So temperature of B will be equal to temperature of C. So condition like this you can write: if TA is equal to TB and TA is equal to TC, then TB is equal to TC. Okay, so this is zeroth law of thermodynamics. Okay, this zeroth law helps us in temperature measurement. Helps in temperature measurement, and this temperature during this temperature measurement body C या फिर और वी कैन से द acts as body A. Okay, it means that thermometer will have to like be in thermal equilibrium with two different bodies. Okay. Next, we will talk about types of thermometer. Types of thermometer. So, in types of thermometer, first we have to talk about thermometric properties. Thermometric property. So, what is thermometer metric property? So, thermometric property is a property which helps in finding out temperature okay. Example, what is the example of thermometric property? Like volume or length of mercury thermometer. Okay, so the first type of uh, thermometer we will look into is a resistance thermometer. Okay, so for resistance thermometer we have a simple circuit like this. We should you have studied the simple Wheatstone bridge in your initial 12th class. Okay, so let's say this is the Wheatstone bridge. This resistance is P, this is Q, this is a rheostat R, and this is S. Okay, so this is made up of platinum wire, and let's say this S resistance is placed in at site where we have to measure the temperature. So from Wheatstone, assuming Wheatstone bridge, when we make the current in this circuit to be 0, we can say that P by Q is equal to R by S, and we will be able to calculate S, value of S. Okay, and this resistance thermometer, we can say that it uses resistance as a thermometric property. Resistance as thermometric property. Okay, so this resistance thermometer, I mean the temperature S can be written as S is equal to A plus BT in terms of temperature, where T is temperature. Okay, so we can express S is equal to A plus BT. So whenever we will get the value of S, we can calculate the corresponding value of temperature. Okay, though, so the second type of thermometer is thermocouple. So thermocouple acts on the principle of Seebeck effect. So what does it explain? What does it tells? It tells us that if there is a temperature difference between 2 points, like say this is temperature A, it is temperature B, and TA is not equal to TB. TA is not equal to TB, and if they are both joined with the help of wire or metallic wires. Let's say we have joined both T and TB with help of metallic wire. So what will happen that between A and B, the EMF will generate. Okay, so this EMF here will act as thermometric property. Okay, and this EMF is directly proportional to change in temperature. I mean, sorry, not in change in temperature, difference of temperature. That is, delta T here will be equal to like TA minus TB. Okay, or TB minus TA, whichever is eligible here. So next, we will move to like similar to Seebeck effect. There is another effect which you should have studied. That is Peltier effect. Sorry, Peltier effect. Okay, so what is Peltier effect? Peltier effect is opposite to Seebeck effect. In Seebeck effect, it tells us that if there is a temperature difference available, then there will be a EMF generation. But in Peltier effect, we see that if there is a EMF or like voltage applied across 2 points, okay, so there will be a temperature difference. Like what we have done like connected a battery between point A and B. Okay, so there will be temperature of the 2 points will be different. Okay, so TA and TB, and let's say TA will be less and TB will be more. So one end will be cold and another end will be hot. Okay, so this is used for thermoelectric refrigeration. You should remember this thing. Peltier effect is useful in thermoelectric refrigeration. Okay, next so next third type of thermometer we will study is constant volume gas thermometer. Constant volume gas thermometer. Okay, so what is constant volume gas thermometer? Like say if the flow through a or flow or like say there is a rigid container. Okay, and there is a rigid container, and let's say it is connected to a pressure measurement device P. Okay, or pressure gauge, and since the container is rigid, what we can say here that volume is equal to constant, hence pressure is directly proportional to temperature. So P1 upon P2 is equal to T1 upon T2. Okay, and here since it is constant volume gas thermometer, as pressure is our thermometric property. If we talk about the constant pressure gas thermometer, that is next fourth. Thermometer. So let's say that this is a cylinder piston arrangement. Okay, and it is piston. So what we can say for sure here that let's say since the pressure is constant, So volume will be directly proportional to temperature, and V1 by V2 is equal to T1 by T2. And from this we can say for constant pressure gas thermometer, volume is thermometric property. Okay, so both constant volume and constant pressure gas thermometer are called ideal gas thermometer. Okay, so let's see what is ideal gas first. So we will discuss what is ideal gas. Ideal gas. So what is ideal gas? For ideal gas, we have a few assumptions. That is, assumption number one is, let's say assumption number one is negligible intermolecular forces. Intermolecular forces. Okay. The second is volume occupied by gas molecules is negligible compared to container volume. Container volume. A real gas, which is like air, is will act as a ideal gas when there are two conditions. Let's say the favorable conditions. Favorable conditions for ideal gas. You should remember these 2 points, they are very important. First is low pressure. Low pressure. So pressure is generally generated due to uh, collision of molecules with the surface. If there is negligible intermolecular force, then what will it mean? It will mean that there is very less number of molecules, so the pressure will be very less. The second is temperature. That is high temperature, very high temperature. Okay, so these two are very important regarding favorable conditions for ideal gas, and the most important is low pressure. Okay, so all substances naturally existing as gas like oxygen, nitrogen, helium, argon should be considered ideal gas in the all the further questions which we will be doing. Okay, and one point you should remember that steam is not ideal gas. Okay, steam cannot be considered as a ideal gas unless it will be like helpless situation. There is nothing given in the question. Then, if the question is like we can also only consider steam as a ideal gas, then only we will consider it. Okay. So, what is the equation of ideal gas? Ideal gas equation, most famous equation is PV is equal to MRT. Okay, pressure, volume, mass. Okay, R is characteristic gas constant. Gas constant, and its unit is kilojoule per kg Kelvin. Okay, and in another way we can write PV is equal to N R bar T. Okay, so N is number of molecules, okay, and R is the universal gas constant. Universal gas constant, and its value is R bar is equal to 8.314 kilojoule per kilo mole Kelvin. So here the number N, that is number of moles, is generally written is kilomole. Okay, and this characteristic gas constant is related to universal gas constant by relation R is equal to R bar upon molecular weight of gas. For air, this molecular weight is 29. So when we calculate R, it is 0.287, which we will discuss later. Okay. So one thing you should must remember is that ideal gas thermometer are independent of material of construction. Okay, like if it whether it is considered from any material. Okay, so like see here, for constant volume gas thermometer, the thermometric property is pressure, and for constant pressure gas thermometer, the thermometric property is volume. Okay, so it is independent of the material, unlike in the case of like thermocouples. uh, on the basis of the material, the EMF will be generated, and in case of resistance thermometer, the resistance will be generated on the basis of the material of the resistance. Okay, so the most important point is ideal gas thermometers are independent of material of construction. That is, it doesn't depend on upon which gas is used. Gas is used. Okay. Next topic we will discuss is temperature scales. Temperature scales. Okay, so in temperature scale there are basically three times. I mean, in generally there are three types of scale which are in generally used in regular life. Okay, so let's start with these three first. So let's say we will draw some reference points. This is steam point. Okay, and let's say this is ice point. Okay, let's say there is some intermediate line, some intermediate is at some particular temperature. Okay, so so at the in like Celsius scale, 0 degree Celsius is referred as ice point, and 100 degree Celsius is referred as steam point, and let's say that some TC temperature is intermediate temperature. Okay, if we came to Fahrenheit scale, in Fahrenheit scale 32 degrees, let's write it some other color. 32 degree Fahrenheit is ice point, and 212 degree Fahrenheit is your steam point, and let's say some TF is the intermediate point. And if we talk about the Kelvin scale, in Kelvin scale, let's start with the 0 degree Celsius. So at ice point it is 273.15 Kelvin. Okay, and at steam point it is 373.15 Kelvin, and let's say that is there is some temperature T which will be in Kelvin, intermediate. Okay, so we can like if it is asked to convert the temperature scale from degree Celsius scale to Fahrenheit scale, we can do it by interpolation only. Let's say that temperature Tc minus 0 upon 100 minus 0. Okay, this difference upon this difference, we will equate for both degree Celsius and Fahrenheit scale. Okay, so Tc minus 0 upon 100 minus 0 is equal to Tf minus 32 upon 212 minus 32. So from here we will obtain Tc is equal to 100 upon 180, that is 212 minus 32 into Tf minus 32. Okay, so as we can derive from here, Tc is equal to 5 by 9 times of Tf minus 32. So this is the relation for conversion of temperature conversion from Fahrenheit scale to Celsius scale or vice versa. Okay, in Kelvin scale we write temperature in Kelvin is equal to temperature in degree Celsius plus 273.15. We can also write it in like similar way as we have written the above equation, or it is basically the Kelvin scale is derived from experiment. Okay, so this Kelvin scale is also known as absolute scale. Kelvin scale is also known as absolute scale. Okay, so this Kelvin scale is the most important point. All the other as we discussed the steam point or the Celsius scale or Fahrenheit scale, we discuss them with the reference of like 2 point, steam point and ice point. Okay, but for Celsius scale, it can be absolutely derived or can be written with a single point of reference. And what is the single point of reference? The single point of reference is triple point of water of reference. Okay, triple point of triple point of water. Okay, so we will write the definition of 1 Kelvin. So 1 Kelvin is equal to 1 upon 273 upon 1/6 of triple point temperature of water. So this is with the value of 1 Kelvin. Definition of 1 Kelvin if you are asked. Okay. Next thing, we will see if we draw. So how is Kelvin scale came to being? Okay, so the scientists experimented the temperature for various gases. Okay, so let's say that this temperature axis and this is pressure axis at different pressure. Okay, so let's say there are three gases we will going to study here, about three gases. Let's say first is gas A, which is at for 100 degrees Celsius. Not only gases, for any fluid, like say for any fluid, if it is at 100 degrees Celsius. So we have already seen the definition of 1 Kelvin, that is 1 upon 273.16 Tth of triple point temperature of water. Okay, for let's say for water only at 100 degrees Celsius from steam point, we will measure its temperature with the help of three different thermometers. Okay, let's say thermometer A, thermometer B, and thermometer C. Okay, so this will be the if we decrease the temperature of the water, the thermodynamics will thermometer A will show temperature on this line. Okay, and corresponding pressure of course, and this is for thermometer B. This is for thermometer C. Okay, now if we freeze the water, decrease the water temperature from below the 0 degree Celsius, or we can extend the three lines. When we will extend these three lines, we will converge to a single point. This is observed experimentally, and uh, this point will be known as temperature absolute temperature, or absolute temperature, or let's say absolute zero. So this will be our 0 Kelvin. Okay, and that is minus 273.15 Kelvin. And this is our 0 degree Celsius, that is 273.15 degree Celsius. And here at some point we will obtain a triple point of water, which is 0.01 degree Celsius, or like said 273.16 Kelvin. Okay, so for Kelvin scale, from here we can say for any thermometer, for Kelvin scale we can define whole temperature range with only a single reference point, that is 0 Kelvin, and which is also known as absolute zero. Okay, and you should remember this thing. Okay, here like I have drawn here. So there are many questions asked where you will be provided with a random like temperature scale, and you will be asked to like correlate both of those temperature scales. So you will use these like tactics like this, these tactics to overcome your difficulties there, and you can directly get the answer. Okay.